Okay, so this is going to be the synopsis of just the beginning part of this generation of electrical power using heat engines. So just the part that I did in class on Thursday, August the 27th. The rest of this, we'll pick it up with the Rankine cycle next Tuesday. Okay, so for that introduction, I went over this little thing. It's worth reading and just thinking about this little bit about the role of the Enlightenment in classical physics and how we got to an understanding of thermodynamics that was really driven by the heat engines, the steam engines that were being built by people that didn't really understand the science behind it. And so the science had to catch up to the technology. And then later, when we start to talk about generators and have to understand at least a little bit about Maxwell's equations, then we'll see that it went the other way around, that things are more like how we experience them now, where there was science that was developed and understood, and then sometime later, technology started to grow out of that. Okay, but back into our main topic. This is our high-level schematic. So we're going to have some kind of fuel, maybe coal, it may be natural gas, it may be nuclear reactions that are creating heat, but we're going to have some kind of fuel that's putting heat energy into the working fluid of our heat engine, which for this first thing we're going to talk about the Rankine cycle, we're going to put heat energy into water and we're going to make steam. All right, so we have some energy in, which is the thermal energy released by the combustion of the fuel or by the nuclear reactions that go in. We're going to have this heat engine then that creates that converts that heat energy into mechanical work. And then we're going to have a thing that right now we're just going to pretend is a black box. It magically takes mechanical work in and it gives you electrical energy out. So remember that the efficiency here is the energy out over the energy in. The energy out is going to be the electrical energy output by the generator. And also, if I tell you that a plant is, for example, a 1,000 megawatt plant, the 1,000 megawatt is the full capacity power output, and it is the full capacity electrical energy power output. So don't get confused and think that the 1,000 megawatt power plant has 1,000 megawatts of thermal energy in. It has 1,000 megawatts of electrical energy out. And remember, that means we're going to have more. Now, I keep saying energy, I really mean power. We're going to have more than 1,000 megawatts of thermal power in because efficiency is not going to be 100%. Okay, so that's our top level diagram, our schematic. And we're going to talk about different heat engines that can go in this middle part. And the first one we're going to talk about is the Rankine cycle, which is a steam engine that creates mechanical work that then connects to the generator. All right. Remember, efficiency equals energy out over energy in. There's three things there. There's efficiency, there's energy out, there's energy in. If you know any two of those parameters, then you should be able to find the third one. And once again, just remember, energy in is always, always, always greater than energy out. Okay, make sure that's true when you do your calculations. So you might think I'm hammering this a little too hard, but I could tell you every year I teach this class, somebody tells me I got 1,000 megawatts of electrical energy out, and I only put 900 megawatts of electrical power or thermal power in. So make sure you clearly understand there has to be more power in than there is power out. There's all kinds of ways and problems I can give you the efficiency. I can just tell you what the efficiency is, and that'll make life easy, depending on what I ask, of course, but I could just tell you what the efficiency is. I could give you T hot and T cold, and then you could calculate the Carnot efficiency, and then you could estimate that this particular power plant is going to get something like 1/2 to 2/3 of the Carnot efficiency. I could give you the electrical energy output and the amount of fuel burned to get this output. So then you're going to have to calculate how much heat energy was in that much fuel. And then you can calculate the efficiency. So there's multiple things or multiple pieces of information I can give you, and then you need to be able to find the efficiency from those pieces of information. So think about that. Make sure that you have some inkling of how you would do it, depending on what kind of information I give you. We also went over the relationship between power, energy, capacity factor, and you need to know these relationships and know that everybody sometimes mixes them up when I talk about them. I bet you 5 times already in this little synopsis, I've mixed up power and energy. But, but remember, energy is power times time. So if something is running at a constant level of 100 watts for 1 week, the amount of energy would be 100 watts times 24 hours times 7 days, which would be 16,800 watt hours or 16.8 kilowatt hours. And then, depending on what you're asked to calculate, you might have to convert that into joules. So I tell you it's a 1,000 megawatt power plant. That's the power that's out, that goes out. It's, if it's at running at full capacity, that's going out all the time. If I wanted to ask you about energy, I would have to tell you over what time period. So make sure you understand that relationship. Capacity factor tells you what percent of the time a plant is running at full capacity. So if it truly runs at full capacity all of the time, the capacity factor is 100%. No real power plant has a capacity factor of 100%. Nuclear power plants get pretty close. They get up in the 90s, but nothing will run at 100%. There's going to be maintenance, changing of fuel rods, things like that that are going to happen, that are going to always pull that capacity factor down under 100%. If a power plant runs at full capacity half the time and at zero the other half, the capacity factor is 50. If it runs at half of full capacity all the time, the capacity factor is also 50%. So there's all kinds of things that could happen. You could have a plant that's running at 50% of capacity for some percentage of time, and 25 another percentage of time, and 100% another percentage of time, and zero for some percentage of time. And then you would have to calculate what the actual capacity factor would be for that particular case. Okay, so make sure you know those relationships. That's going to make talking about power plants much easier for us if these things aren't hanging you up. Okay, so the first thing we're going to talk about is making electricity by burning a fuel and making steam. And this is called the Rankine cycle. And in class today, we just went over very briefly when we went over the schematic. So let's look at the schematic here in the synopsis. So here's the schematic. So here's an actual schematic, and here's something that's a little bit more of a cartoon of what a Rankine cycle power plant looks like. But if we can, you can always start anywhere in these cycles. These are circular cycles. But let's just start here. So this is cold water, at least relatively cold water, that is at low pressure. And it's going to go through a pump. And this pump is going to put the water under pressure. So now we're going to have high pressure water. It's still cold, but now it's high pressure water. And that high pressure is going to do a couple of things. One thing it's going to do is it's going to push this working fluid, the water and the steam is going to push it through the system. But it's also going to change the boiling point of the water. So if we pressurize the water, it's going to boil at a much higher temperature. This pressurized water is going to go into a boiler. So here the water is going through some serpentine set of pipes, and we're burning a fuel. Maybe we're burning coal here. And as this water passes through this boiler, you will eventually turn into steam. And when you leave this outlet port up here at point 3, that steam is going to go into a turbine. So we're going to have steam expanding and cooling, and that loss of energy from the steam is going to be turned into mechanical turning of the turbine. That turbine will be connected to a generator that's going to make the electricity. But when the steam has gone all the way through the turbine and comes out the other end, then we're going to condense it. So we're going to have some heat loss here as the steam condenses into water, and then the cycle will start back over. Right, so take a look at the schematic, both this pictorial version and this actual schematic version, and make sure that you understand what's going on and what's happening at the different places. That's where we ended today, and then tomorrow we're going to pick up and we're going to start talking about what happens as we start heating up this pressurized water and turning it into steam. Okay, that's it for this synopsis.